Hello everyone. In this lecture now we're going to look at the mesh analysis and consider a situation or a case where following the normal steps that we discussed earlier is actually not going to work properly, and again we're dealing with an exception that we have to find a workaround. And then also I'm going to show you how to go back and use the universal method, which as we discussed we hope for is going to work regardless of what circuit you're dealing with. Okay, so this is the circuit, and with the mesh analysis, if you recall, we don't identify nodes. Instead, we identify what we call loops or meshes. So there's one loop or mesh here that I can identify, and again the direction of the current passing through the loop is arbitrarily chosen. So I'm going to call this I1 and call this I2, and then I start going through each loop, and every time that I pass a component and go to a higher potential, I'm going to add the potential. Every time that I pass a component and I lose potential, I subtract the potential. So I go through the loop, start from a point, add and subtract potential voltages, then I get to the same node and I equate that to 0, obviously because I'm back to the same potential. So that's set. With this one, I'm going to start from that point right there. So in the direction of the current, if I pass through a resistor, I'm losing potential. So this is mesh. That would be minus 3 I1, and I get to this current source immediately, and I have to write the potential difference across the current source in that mesh. But as you recall, for a current source, the current that is passing through the source is known, but there is no equation that describes the voltage across the current source, and therefore I'm stuck right here. Like, I don't know what comes next. I either have to identify a new unknown and move on, or I have to find a workaround. So now the workaround that is going to work here, and it goes like this. So we basically define a new mesh through which I'm going to bypass the current source. So look at this. So if I define a new mesh as being a loop that goes like that, but it actually doesn't go through that current source anymore, right? So I no longer going through that new loop. I'm not going to pass through this current source, so no longer need to know what the voltage across that current source is. This new mesh or loop is called the super mesh. So this is equivalent of the super node. With the super node, we defined a node that included more than one node, and the motivation was to include the component with an unknown current, unknown equation for current, inside the super node so that I don't have to deal with it. And here the motivation is exactly the same, but a dual of that in the domain of voltage as opposed to current. So this super mesh includes more than one mesh, one normal mesh, and the motivation is to define it such that I don't have to count for the voltage across a component for which I don't have an equation for, in this case this current source. So I'm going to now, instead of writing equation for those two individual loops that or meshes that I identified originally, I'm going to go through this new loop and write the equation again. So starting from the same point, I have minus 3 I1 passing through the 3 amp. The current is I1, and so the voltage drop would be minus 3 I1. Then I get to the 2O, and there the current that is passing through is actually I2, so I have minus 2I2 the drop of voltage across the 2, and then I have the voltage drop of 50 volts, and I go through this source. Then I get here, I have another voltage drop of 4 times I2. For the 4 ohm, I get to the 6 ohm, I have another voltage drop of 6 I1, and then finally I get to the 100 volt, and I have the voltage 100 volts, or gain 100 volts of potential. So this would be the equation for the super. So this is for the super mesh. Okay, so now as you notice, I don't need to know what the voltage across the current source is. Now I get one equation but two unknowns. Therefore I can't calculate I1 and I2 yet. But there's one more thing that I know about the circuit, and that's the equation for the current of that source. See, I don't know anything about the voltage of the current source, but I do have a statement that tells me what the current is, and that's obviously 5 amp. Now 5 amp as a function of the unknown currents that I've defined for my circuit gives me the second equation that I require. I know I1 is going down and I2 is going up, right? And you add the two up and you get the 5 amp current that is going up, right? So I2 minus I1 is actually equal to 5 amp. Okay, so now with these two equations, now I can conclude my analysis for mesh using the concept of a super mesh and calculate I1 and I2, which is at this point is a simple calculation. I2 is equal to 5 plus I1. I put it in there and I can calculate both I1 and I2 at that point. Now, let's resort back to the basic universal approach and see how we could have done that without really resorting to defining anything, any new concept. So with our method, we have to actually define nodes. That's one node, that's a node, this is a node, that's a node, node, node. Then I'm going to take one of these as my reference. This would be my 0 volts. At that point, this becomes 100 volts. This would be V1. And call that V2. Call that V3. And then I can call that either V4 or write the equation for this component right here and avoid basically defining a new unknown voltage. And that would be this voltage minus that is 50 volts, which means that voltage is V3 plus 50. Okay? Then I define currents. I'm going to call that I. Since I already used I1 and I2, I'm going to use different notation for this one so that they don't get confused. So this is IA. This would be the same IA. Obviously, this is 5 amp. This, I'm going to call that IB. Therefore, that would be IB, KCL for that node. This would be IB, again, KCL for this node. And this, I'm going to call it IC, and I'm done. I have defined all the currents and voltages in the circuit. So with that, I'm going to start writing KCL. So KCL, I have 1, 2, 3, 4, 5, 6 nodes. I don't have to write KCL for this one. And by the way, actually at this point, since I defined this as a different, I could have actually written an equation, a KCL equation for this one, and avoid calling that a new current. So that would be IA and IA, the same current with the KCL. So this all have the same current, obviously. So I don't have to write KCL for any of that. There's a KCL for that node and KCL for that node. So IA going into that node, 5 amp is going to V1, and then IB is leaving that node for the node down here. IB is going in, and it's 5 plus IA. So you notice that since I actually called these two the same current, the two KCL for these two nodes became redundant. Basically, I only needed one KCL. The reason is that I already wrote a KCL for that ground. And if I didn't and would call that IC, then I would need another KCL for that one. But at this point, just one KCL would have been enough. Although writing KCL for any external node is still correct, but like you see, it's redundant. So again, I could have called that IC as opposed to writing a KCL for this, then write KCL for that node, and the two KCL would have been different. But since I actually did KCL for that ground node, which I wouldn't normally do, then this node, the KCL for that node, became redundant. So now, equations for components. I have 1, 2, 3, 4, 5, 6, 7 components. Equation for that component source and this one and the current source, they are all done. So I'm only left with 4 components to write equation for. IA, Ohm's law for that would be 100 minus V1 divided by 3. IB would be V1 minus V3 plus 50 divided by 2. For the 4 ohm down here, IB would be V3 minus V2 divided by 4. And finally, for the 6 ohm, IA is equal to V2 minus 0 divided by 6. So let's count the number of unknowns. IA, IB are the two current unknowns, and V1, V2, and V3 are the 3 voltage unknowns. So total of 5 unknowns, and I have 1, 2, 3, 4, 5, 6 equations, which is more than what I really need. Let me make sure that I counted everything correctly. I think I did. We have V1, V2, and V3 as the voltage unknowns, and IA, IB as the currents unknowns. So by solving this set of equations, by the way, we already know why we have one more equation than one we need, because these two equations are actually the same. So these, we don't have to count that as a new equation. So this is a redundant equation. So 1, 2, 3, 4, 5 equations and 5 unknowns, and that should solve our problem, and every unknown in the circuit would be calculated. And now notice again that with this, we really didn't need to define anything new. You can actually show again that this equation for the super mesh is a result of combining these equations together, and by combining them together you get the same equation. So the beauty of using this algorithm is that it just works no matter what kind of situation you're dealing with. With this one, you had to only solve 2 equations, whereas here we have 5. But then at the same time, once you're done calculating that, you only get this current and that current, and you have no knowledge of actual voltages for the nodes, and then or voltages across the components. So if you need to calculate those voltages, you have to continue. So in terms of how different the two are, in terms of how much time it takes, if you only look for currents that are passing through components, certain currents passing through certain components, then mesh analysis would be faster. But if your ultimate goal is to completely analyze the circuit, this would always work and give you all the values at the same time. So with that, I conclude this lecture, and we are going to do more practice with circuit analysis using these different methodologies later in the next few lectures. Thank you.